Welcome to the Explainer. Let's just dive right in, because today we are setting out to decode absolutely the most critical, world-defining technology of our era. I'm talking about the semiconductor. It's literally the invisible bedrock of modern human progress. We're going to take an incredible journey today, zooming all the way into the mind-bending quantum mechanics of single atoms, and then pulling all the way back out to the massive macroeconomic forces driving a trillion-dollar global market. If you want to understand the modern world, well, you've got to understand the silicon that runs it.
To ground us, here's a familiar sight, a CPU. But what's truly staggering is the sheer scale of what this represents. Get this, the global semiconductor industry produces over 1 trillion of these chips every single year. Let that number sink in for a second. Over 1 trillion chips a year. They act as the hidden brains powering absolutely everything around us. From that smartphone sitting in your pocket right now, to the massive data centers training tomorrow's artificial intelligence. They are, for sure, the heartbeat of our modern global economy. So here is our roadmap for today. We're going to cover 1. The hidden brains of technology. 2. P-type and N-type magic. 3. The journey from sand to microchip. And finally, 4. The future of semiconductors. All right, Section 1, the hidden brains of technology, controlling the flow of electricity. At its very core, modern electronics faces just one fundamental problem. To process data, we have to be able to control the flow of electrical current, right? We need to turn it on and off billions of times a second without a single fail. And this brilliantly illustrates exactly why semiconductors are the perfect solution. They sit right midway between conductors, like copper, which just lets electricity flow freely, and insulators, like glass, which blocks it completely. Now, silicon is the undisputed king here, and it's all because of its atomic structure. It has exactly 4 valence electrons in its outer shell. This unique property allows it to form a perfectly stable crystalline framework. On its own, it doesn't conduct much. But because that lattice is so incredibly stable, we can step in and precisely manipulate it to do exactly what we want. Which brings us to Section 2, P-type and N-type magic, the microscopic architects. This is where we step into the shoes of the engineers to perform a process called doping. Essentially, doping is the intentional, highly controlled introduction of specific impurities into that pristine silicon crystal to totally change how it conducts electricity. We categorize this doping into 2 distinct types. On the left, we have N-type doping. Here, we use group 5 elements, which have 5 valence electrons. When they lock into the silicon lattice, they act as electron donors. Basically, they leave one extra free-flowing, negatively charged electron roaming around. Then, on the right, we've got P-type doping. For this, we use group 3 elements, which only have 3 valence electrons. This creates a positive vacancy, or what physicists call a hole. Think of this hole kind of like an empty seat in a packed movie theater. As people, or, electrons, move to fill the empty seat itself appears to move through the material, acting as a positive charge carrier. Pretty cool, right? So the absolutely crucial point here is choosing the right element for the job. If an engineer wants to boost negative conductivity, they'll pull an N-type element straight from the periodic table, like phosphorus or arsenic, because those 5 valence electrons guarantee an extra donor electron. But if they want to create those positive holes, they'll use a P-type element, something like boron or gallium. By fine-tuning the exact concentration of these specific elements, engineers can dial in the precise electrical properties they need for any specific chip. But the real magic? That happens when we bring these 2 together. When an N-type and a P-type semiconductor meet, they form what's called a p-N junction. Electrons from the N side practically rush over to fill the holes on the P side, creating a boundary called a depletion zone. This establishes a built-in electric field that acts exactly like a microscopic one-way valve for electricity. I cannot stress this enough. This p-N junction is the foundational building block for every single diode and transistor in existence. It is literally the physical basis of all modern digital logic. All right, Section 3, from sand to microchip, the manufacturing journey. Now that we understand the atomic physics, let's zoom back out to the factory floor. Because it's one thing to design these structures on a computer screen, it is a completely different, mind-boggling challenge to physically build these microscopic features at scale. Let's briskly walk through this highly satisfying manufacturing sequence. Step 1, we start with literal sand, melting it down and purifying it until it's 99.9% pure monocrystalline silicon. Step 2, we slice that crystal into ultra-thin, perfectly polished wafers. Step 3, We deposit insulating layers and use extreme ultraviolet light in a process called lithography to print unimaginably intricate circuit patterns right onto the wafer. Step 4. We etch away the excess material and use ion implantation to dope the silicon with those P and N-type elements we just talked about. And finally, step 5, the whole shebang is tested, cut, and packaged for the real world. Now, all of these delicate processes demand extreme cleanroom conditions. We are talking about environments exponentially cleaner than a hospital operating room. Why? Well, because the transistors we're printing are measured in nanometers, billions of a meter. A single speck of microscopic dust falling on a wafer during lithography is like a massive boulder crushing a city street. It can completely ruin an entire multi-million-dollar batch of wafers in an instant. As we continue to shrink transistors down to the single-digit nanometer scale, traditional manufacturing hits some serious physics limits. For example, shooting high-energy ions into silicon to dope it can actually violently damage that delicate crystal lattice we need, requiring massive heat to repair it. To get around this, engineers have had to invent incredible new techniques. We're talking about things like atomic layer doping, which deposits impurities one single atom at a time, or plasma doping, which acts like a magical atomic-level spray paint to perfectly coat complex 3D transistor structures evenly. It's wild stuff. Section 4. The future of semiconductors, a trillion-dollar market. Let's shift gears here and take a look at the staggering global economics that are actually funding all this cutting-edge physics. In 2024, the global semiconductor market sat at a massive $627 billion. But fueled by the explosive, relentless demand of our digital age, it's projected to grow at an 8.6% compound annual growth rate, meaning it's on track to smash right through the $1 trillion mark by 2030. The real heavy hitters driving this growth? Server and network AI, growing at an astonishing 11.6% annually, with the automotive sector right behind it at 10.7%. And speaking of the automotive sector, this microscopic physics connects directly to your daily life. The car of the future is no longer just a mechanical vehicle, it's a high-performance computer on wheels. The total shift towards software-defined electric vehicles, plus levels 2 and 3 of autonomous driving, means the sheer volume of chips needed per car for high-performance computing, sensors, and power management is absolutely skyrocketing. Which leads us to this massive statistic: 60%. By the year 2030, over 60% of power semiconductors in vehicles will transition completely away from traditional silicon. Why? Because electric vehicles require the repeated switching of incredibly high voltages, and silicon simply isn't efficient or tough enough anymore. Instead, the industry is pivoting hard to advanced materials like gallium nitride and silicon carbide. These materials can endure much higher voltages without failing, which prevents EV fires and enables those ultra-fast charging times that consumers are basically demanding. But the innovation doesn't stop there. As we approach the physical limits of what silicon can actually do, researchers are already working on the next frontier. We're looking at things like spintronics, a totally mind-bending field where devices don't just use the electrical charge of an electron, but utilize its actual physical spin state to process and store data simultaneously. We're also seeing the rise of topological insulators, which conduct electricity on their surface but are insulators inside. Plus, there are exotic new compounds like gallium manganese arsenide that could merge system memory and processing into a single, ultra-efficient layer. All of this leaves us with a final, provocative question. We've journeyed from the subatomic manipulation of electrons into the multi-billion-dollar cleanrooms and out into a trillion-dollar global economy. Human ingenuity has mastered silicon to build the modern world. But as we finally approach the physical limits of this amazing element, what new material will power our next massive leap forward? I really hope this explainer has given you a newfound appreciation for the hidden brains powering our lives. Thank you so much for learning with us today.